All right, coming back into part 2 of our video. As you can see, I did finish out the last problem. We had already integrated the x over square root of 4 minus x squared in part B. So I added that in. And then the integration of the 2 over square root of 4 minus x squared was the same as part A, except you had a Rider constant, of course, plus your c. All right, keeping in mind, just kind of going through another example very similar to this, is to look at D, E, and F. I added an extra one to your notes. So again, same kind of idea is that we're recognizing over here that if we have a constant over the 2 plus 9x squared, which is, or in general, let's keep it more general than that, if you have a constant over a squared plus u squared, then that is always going to be an inverse tangent problem, whereas up here, this was always an inverse sine problem. So in this problem, you just identify what your a and your u is. So a is going to be square root of 2. U is going to be 3x because 3x squared equals 9x squared, just kind of FYI. And then you do still want to do du, which is 3dx. We do need a corrector because we are missing the 3 that we need there. So we add in our 1/3. So you kind of are still doing the whole u substitution with the du, and we add our corrector. And then we simply follow the pattern for the inverse tangent rule. So the inverse tangent rule says my corrector 1/3 times 1 over a, 1 over square root of 2, inverse tangent of the u, which was 3x, over the a, square root of 2, plus c. And so that would kind of finish out our inverse, or our antiderivative in that case. All right, now take a look at E. Same kind of idea as what we did with A, B, and C, is that having the x there means it's a completely different problem. This is a u sub problem, not an inverse tangent problem. U would equal 2 plus 9x squared. Du would be 18x. So we do need a corrector in this one. So I add in my 18 and I divide it out on the outside. So my integration is going to be 1 over 18, the integral of 1 over u du, and this turns into a log problem. 1 over 18 natural log absolute value, 2 plus 9x squared plus c, and we're done with that one. So just kind of highlighting my answers here as we go. Now, just as a real quick comment here, these are unnecessary here simply because 2 plus 9x squared is always positive, so you can take those out in that case. All right, and then when I look over at F, again, this idea here is that when you go to do your quote-unquote u substitution, you're going to have extra things. Like if you didn't pay any attention to it, you would go u equals 2 plus 9x squared, du equals 18x, and the fact that you have a minus 3 there, it seems to be messing this up. But you really just need to recognize, hey, I'm just going to split this into 2 problems, and I'm going to treat them as 2 separate problems, 2 plus 9x squared dx. And so the first one we just integrated over in E would give us 1 over 18 natural log 2 plus 9x squared. Then here, minus, notice that I didn't have to do a corrector because it had a 3 in it. So this actually just ends up being minus 1 over square root of 2, inverse tangent 3x over square root of 2 plus the c that we had, and that will finish that problem out. All right, now I did add a couple of things to this. I felt like before I got to the next problem that it was a very challenging problem, and so I thought that I needed to do a little pre-work before we get to it. All right, so add number 6 and number 7 to your notes. All right, now for building up to number 8, there are a couple of things we're going to look at, and one is a kind of recap. I'm going to come over here on the side, and I'm going to recap completing the square. Complete the square, which we did back in Algebra 2. So if I have something like x squared plus 6x plus 11, obviously it doesn't factor nicely, and it's not a perfect square, so it's just a quadratic. that really doesn't have a lot going for it. But one of the things that we can do, a trick for manipulating quadratics into a better form, is to take these terms, the first two terms, and we are going to add something to those terms so that this is a perfect square. That's where the complete the square comes from. And then because we don't want to change it, we take this other constant, we want to subtract something so that the net of these two numbers right here, this minus this, is going to equal 0. So we aren't really changing the problem, but what we're doing is we are manipulating it into a different form. So in the rule for completing the square, excuse me, is that the first thing you're going to do is your coefficient here must be a 1, which it is. Then you're going to take the middle term, b, and you're going to divide by 2, and you are going to square that. And that's going to tell us what we're going to put into the first blank. So 6 divided by 2 is 3, 3 squared is 9. And hopefully you'll recognize that this x squared plus 6x plus 9 is going to factor to x plus 3 squared. It is a perfect square. And now because we added 9 in, we are also going to subtract the 9 over here to balance the equation out so that 9 minus 9 is 0. And we haven't really changed it. We're just putting it in a slightly different form. All right, and 11 minus 9 is 2, and so that would be our completing the square with a 2. Now, just as a kind of side comment about this completing the square, what do you do if there is a coefficient in front of it? So, for example, what if I had 2x squared plus 12x plus, say, 22? Just kind of use the same type of a problem. We actually don't worry about the 22, but what you are going to do is you're going to take this first set right here. You are going to kind of group them together, but you're going to pull the 2 out. So what's inside does not have a coefficient on the x. And then we're going to do our plus 22 minus over here. So you kind of set it up exactly the same way. You just pull out that 2 over here. Now when I go to complete the square, I follow the same rule. Take the middle coefficient, take half and square it, so it would still be plus 9. The only difference here is that when you are bringing down what you actually added into this problem, minus blank, is that when you look at it, the question is, what did you actually add? So what I actually added was 2 times 9, or 18 right there, because of the parentheses. So what I have to subtract is 18 so that it's equal to 0. And so that kind of fills that out, and then we can factor it to 2x plus 3 squared, and then plus 4, and that would be the completing the square if there's a coefficient there. All right, so now that we have that down, let's come back over here to these problems. So I initially see something like number 6, where I have a constant over a quadratic. And I don't even have to do the u substitution because the quadratic is not going to work to be u equals x squared plus 6x plus 11 because the du would have to have a linear term. And I don't have that. And so here, what I'm going to do is I am going to trick the problem and complete the square. So we're going to bring in the work that we did over there, this completed square version, which is the same problem, but in a different form. And then when I rewrite it like that, now I can let u equal x plus 3. Du would be dx. So the 10 is actually a writer, and it becomes the integral of 1 over u squared plus 2 du. Right? And now you have to just like, wait a minute, that still didn't work. But now you're of the form, if I rewrite it this way, 1 over 2 plus u squared du. Do you see how you're in an inverse tangent form? So my a is going to be square root of 2. And so I would be doing 10. And then we have for our inverse tangent, it's going to be 1 over a. So 1 over square root of 2 inverse tangent of u over a, square root of 2, plus c. And then to finish the problem out, we just have to put the quote-unquote u back in. I'm going to erase because I don't really have enough room, but you guys can certainly write another line. X plus 3 is what's going to go inside of that. So it's this idea that we can do this problem, but we have to get it to be in the form that it is a perfect square plus a number so we can use the inverse tangent. So completing the square is going to be our strategy. All right, now let's look at what is a different strategy if the problem has to do with have an x there instead of a constant. So number 6 was a constant over a quadratic. Now we're going to look at x over a quadratic. All right, now in this one, what our problem is if we had tried to do a u substitution, x squared plus 6x plus 11, du would equal 2x plus 6. And so our problem is that we are missing the plus 6 in the du part of this. And, before when we were correcting for a missing constant, we were correcting for a missing constant that was a multiplied constant that was missing. However, what we're going to learn is that we can actually correct for a missing constant that's added as well. What you're basically going to do in this problem is you're going to rewrite it, but you're going to add 0, which is essentially the same thing. Watch this. I'm going to do x plus, now let's think about this. I'm going to do x plus 3 because down here, 2x plus 3 dx. Since I have an x in this portion, I'm matching it to that. And I'm like, hey, it'd be really nice if I had a plus 3 there. But the thing is you can't just change it by adding plus 3. We're going to add the 3, and then we're going to subtract the 3. So that really I have not changed this. The net of these two things is actually 0. So coming down then, what that allows me to do, and I'm going to pause for just a second. All right, so I just moved my completing the square notes out of the way. So now, once I have that, when I split it, it's going to become x plus 3 over x squared plus 6x plus 11 dx plus, or actually in this case, minus, because I subtracted, 3 over x squared plus 6x plus 11 dx. So this portion is just going to be a u subproblem. You would let u equal x squared plus 6x plus 11, du equals 2x plus 6, or 2x plus 3, and of course our dx. So we're going to add in a corrector, 2 and 1/2 to that portion. So the first half of it becomes 1/2 antiderivative of 1 over u du, 1/2 natural log absolute value over x squared plus 6x plus 11, and then we'll do plus c way over here at the end when I fill in the other half. Now in this one over here, you're going to recognize, oh, that was that complete the square problem. So on that one, we're going to complete the square, so it becomes, I'll just come down here, minus, I'll pull the 3 out, the integral of 1 over x plus 3 squared, and what were we, plus 2 dx that we had before. So the 3 is nothing more than an extra rider on that. And so in looking at this is where the 10 was in the problem that I gave you. So that 3, we just do minus 3, and then we would have our over the square root of 2 inverse tangent x plus 3 over square root of 2, and then our plus c. So that kind of shows you where you would take it and split it apart as you're looking at it. All right, so keeping in mind that I have done 6 and 7 now, I want you guys to take a look at number 8. We're going to do a third video on this, and so you're going to try number 8 on your own and then come in after it in the next video and see whether you got it right or not.